All right. I've heard back from a few people about final exam times, and it does sound like we do have overlap for the other parts of the day. So I think most likely our exam will stay from 7 to 10 p.m. at night. Not ideal by any means. Thanks for but I think that that's the way it's going to have to be, just with the number of slots and all the other courses we have going on. Hey, Jose. Can you show up like 2 minutes earlier?
Yeah.
Thanks, appreciate it. All right, so you guys finished the rest of the worksheet that we have for Tuesday, right? So let's go through the answers to those questions. So here's one of those questions. And think about what units you would enter if I had that as an option. This is literally from the end of your last worksheet from last class. So you guys ever want to get access to the worksheets for the slides from class? I always post them after class. There may be a chance that I didn't post them Tuesday after class. Did anyone check right? Okay. I'll post them after class today. I'll post today's and Tuesday's. By the way, best idea ever. If you guys like tea, if you do the mobile order, you can like tell them to add milk to your tea, and they like froth it. It's amazing. Mind blown today. Didn't mean to do that, but really good. All right, everyone clicked in? What are you guys doing?
I really don't know.
So either you can do E, which means times 10 to the, so you can do E minus 4 if you want 10 to the negative 4. Or you could do the little caret, 10 caret, but that's way slower.
Oh wait, you don't have letters? I thought you said to put in the unit as well.
What's wrong with that? What's really wrong with that? You get it done? This was that, I guess, I referenced this figure, but I didn't have a figure in the last worksheet. In the last worksheet, I referenced figure table 14.3, but I didn't include it. All right, everybody in? So, is it going to be, this is a chemical reaction here. There's a lot of stuff going on in this. Hi, Megan. This chemical equation is saying that A reacts with B and forms D and E. So, big picture, the first thing we're going to ask ourselves is the formation of E going to be at a quicker or a slower rate than the consumption of A? Talk to your group for a second. Big picture, is A going to be disappearing quicker or slower than E is appearing?
Slower.
I can't hear you. What do you guys think? Okay, so who can say in one full sentence how A disappearing relates to E appearing? Nice, clean sentence. How A disappearing relates to E appearing.
When 2A and 2B react, the products for E and 5E are created.
Okay, so can someone say the same sentence with time involved now? Mia, can you try?
I was thinking that E is produced at a faster rate than A is.
Consumed?
Yeah.
Why?
I just was looking at the total not exactly.
Okay. Thomas?
So E is produced faster and A is broken down and this is more food.
Okay, so we really need to dig into a more precise way of saying that. Morgan?
So since you need a production of A, B, B, E, and the coefficient of E is 5, which is greater than A, I was going to say slower because you need at least 6A to create 5.
Is that true?
I don't know how to, but I feel like you can't have less reactants.
So maybe what's a little bit confusing is that A is a molecule. There's a lot of atoms in it, and A might have a lot more atoms in it than E does. So when we break apart those 3 A's, that we have enough, with the 2 B's as well, to make the molecules that are shown on the right. So what I really want you guys to be able to say is, in the same time that 3 A's are consumed, 5 E's are produced. And if we say it that way, what's different? The rate of E is faster because the same time it took to consume 3 A's, we made 5 B's. And so I heard a couple people say, well, it doesn't take longer to make, or it takes the same amount of time to make each. Some statement along those lines. But this statement is specifically saying that when 3 are consumed of A, 5 E are produced. So the rate is directly proportional to the stoichiometric coefficient. So that is always the first thing we do when we're looking at relative rates. And then how do we actually calculate it?
I just have a question. I just don't understand what you mean faster and like slower if they're being used to make the E. I don't understand.
So in the stoichiometric ratio, when we combine A and B, we have to have 3:2 ratio, right? And when we put those together, by the time that those are gone, we make 5 B's. So the time that 3 A's went away, 5 E's arrived, or were produced.
So how is the E faster though? Like I just
So in that same period of time, if 3 of these things go away and 5 of these show up, which in the same amount of time is there a bigger change in? Does that help? I think drawing a graph could be a bit challenging. We could say maybe in the first, we could do 2 data points. So we could do time, 0 and 100. And if we start with A, see if I can do this on the fly. Let's say that we have A start at 30. And at time 100, we end up with 0. So if A started out at 30, went to 0, in that time, how many E were made? How do you know it's 50? So we start with 0. How do you know it's 50 that were made?
Because for every 3A, you make 5E, and if you have 30, you multiply by 5/3, and then you get 50.
Circle, dot, dot, come on. So we don't know exactly what the shape of that is, but we could say that if we have 50 up here, oops, I'm not very good at this, am I? This is why I thought it'd be difficult to draw a graph. The rate is a slope, right? The rate is what the change is in a certain amount of time. And during the same period of time, we make a change in 3 of one, we make 5 of the other change, either appear or go away. Does that help at all with the graph?
yeah, but I think I was just a little confused just because the balance.
So I think it's going to be a lot easier when we start looking at actual examples. So let's get beyond this question. If we wanted to calculate this number, how would we do it? Who can concisely tell me how we do this? Demetrius?
Do you just multiply that number by the ratio of 5 to 3?
Yes, but there's an additional step I put in there. Why do we multiply by the ratio?
1/3 of A equals 1/3 of B.
Great. So if we have the rate of A, so what if we divide this rate by 3? What does that give us? We divide the rate of consumption of A by 3. What is that number?
The rate of consumption of 1 mole of A.
So that's if we had something with a stoichiometric coefficient of 1, then this number divided by 3 would be the rate that would be consumed. Everyone okay with that? We don't have something with a stoichiometric coefficient of 1, but that's a really useful number because now we can scale it up to 4 for D, to 5 for E. That's called the rate of reaction. So the rate of reaction is to take whatever the speed of a particular reactant is being consumed at. We divide it by a stoichiometric coefficient, and we say, well, that's our lowest common denominator. Then we can scale up to the consumption or production of any of our reactants or products. And then we know that 5 times the rate of reaction, our xn is reaction, by the way, equals the change in concentration of E over change in time, or the rate of production of E. So once we know the rate of reaction, we can calculate any of the other rates. So when I do these types of problems, I always find the rate of reaction, and then once I have the rate of reaction, then I can extrapolate to any of the other variables that we're looking at. Question?
So why didn't you divide by, if you're doing rate of A first, why didn't you divide by 3 and then multiply by 5? Why is it divide by 5 and then divide it by 3?
This is the units, meters per second.
Oh, okay, I thought that was
Nope. And then I multiplied it by 5 afterwards.
okay.
So once we find the rate of reaction, which is taking the rate of consumption or production of anything divided by their stoichiometric coefficient, we find the rate of reaction, and then we can factor that back up to whichever of the individual things we need. Mia?
Then what's this formula where you have the K value?
We're getting there. We'll be working with that today. Quick question?
I don't know if I'm doing this backwards, but I divided 5 by 3 and then multiplied it by the consumption rate. Does that do the same answer?
So if we take 5.7 times 10 to the negative 4th molar per second, I'm not going to write all the details, times 5 over 3, divided by 3 times 5. That's why this works.
Okay.
I don't want you just plugging in a fraction. I want you to see, well, this is letting us find the rate of the reaction, and then we're scaling it back up to that particular reactant or product.
So just to clarify, so you divide by the coefficient of the reactants and then you
To
multiply
find the rate of reaction.
to find the rate of reaction, and then once you get that, you multiply by the coefficient on the.
We scale it back up. Well, either side. We could say, well, what's the rate of consumption of B? What is that? How do we find that? We take the rate of reaction and we multiply it by 2. What about the rate of production of D?
Oh.
We multiply the rate of reaction by 4. And then we can put a sign there if we want. If we just say, what's the rate of D changing? We might want to say, well, it's a plus because D is being formed. It's an increase in concentration. If it just says, how fast is it going away? We already know it's going down, so we don't have to put a sign there. So the rate of reaction is, how would we find the rate of reaction? 9.5 is, that's the rate of production of E, right? So I think that you guys all found the rate of production of E. 9.5 times 10 to the negative 4th. Oops. So the rate of reaction, though? What is the rate of reaction, Mommy?
The rate of reaction would be the production over the coefficient.
Okay, so about 2 times 10 to the negative 4th? It's like 1.85 or something? Okay. So let's see if you can apply this to one more problem. And I want you doing it in those steps that we just did. Which one do you want to click in? Let's do B. What's the rate of consumption of B? Click in B. Do about 30 more seconds. If you're not sure how to do this, make sure you're asking people around you or raising your hand so that Carol or I can come around. Push, yeah. Oh, I think that's sorry. All right, so how do we find the rate of reaction? That's the first step we have to do here. Jose, how do we find the rate of reaction?
Take the rate of disappearance of it and divide it by the equation.
We're dividing it by the stoichiometric coefficient. So the rate of reaction is?
Or the rate of reaction.
The rate of reaction. Everybody agree? 10 molar per second is the rate of reaction. Everybody agree?
No.
What is it? 5. So the rate of A going away is 10 molar per second, and the rate of reaction is half of that. And then how do we find the rate of consumption, or the rate of B? McKenna? It's 3 times the rate of reaction, because there's 3 that go away for every equivalent of the stoichiometric ratio. So that means that we would have 10 molar per second. That's a second, not a 5. Divided by 2 equals 5 molar per second, and that's the rate of reaction. Once we have that, we say, okay, rate of reaction times the stoichiometric coefficient equals the rate of B. The rate of reaction is never positive or negative, so what would our sign be for this answer? If we just said the rate of B, what are we going to use, Megan? Is the rate of B positive or negative? Whose answer was that? Good job, Shane. Okay, so I didn't say the rate of disappearance of B, so I don't know which direction B is going. So if I'm asking you for what's the rate of B, then you should tell me it's going down. We're decreasing the concentration of B. What would be the sign of C, the rate of C? That's going to be a positive. Devontae?
Is there just like an equation?
Nope. I'm not going to. So I intentionally do this. I intentionally don't give you an equation. Your book has equations. If you want to, you can go read about equations there. I want you logically speaking through the stoichiometric ratio, what that means about A going away compared to B compared to C, and that's based on conservation of mass. And once we have that, we should be able to back out what the relative rates of these things are.
So when something's being consumed, you report it as negative, but if it says it was disappeared at this rate, it would be positive?
Yep. So if I'm saying, what's your speed of your car? And I'm going a certain direction, then I can talk about the directionality being the sign. So if I'm saying, how fast are they coming towards me? Or how fast are they going away from me? Then you don't use what direction they're going, because you're already implying that, and it's going up or going down. All right, so in the rest of the class, we are going to be working through some kinetic stuff that hopefully you guys have done a little bit of in your pre-class quizzes. So we're going to have you determine the order, the rate order using experimental data, which is what we have to do in order to talk about predicting what's happening in reactions. I want you to be able to define a rate law, solve for the rate constant, which is that little k that we were talking about earlier. And we're also going to start talking about determining the rate order not only from data, but also graphically. And there's a few different graphs that we're going to be looking at for that. So when we're talking about making these predictions, Tuesday I liked the discussion that we had that said, there's a lot of times where we care about how a reaction proceeds, about how fast it proceeds, whether that's getting a toxic drug out of your system, whether that's combusting fuel, whether that's rusting of something, whatever it is that's happening, or alcohol metabolism. We want to know how long it takes until something happens. So the first thing we're going to do is we're going to say, well, how does the rate of reaction change with concentration? So what we did as scientists is we said, okay, well, let's control where we start. Let's start with a known concentration of whatever reactants we have, set them up, and then say, go. And when we do that, we want to say, well, right away, can we figure out what the rate of that reaction was? So which of these data points would you want to use in order to talk about the initial rate based on the concentrations we started with? Which is the most useful of these? Which one would you use, Dana? Why A?
Because it's like, you get into the initial.
So if we're talking about based on what our initial concentrations were, how fast did that reaction start? How quick does it go? And if we know exactly how much we started with, by the time we're down here, we don't know necessarily, it's not as easy to figure out how much of each we have. So we're always going to be, in the next section of our class, we're going to say, well, what happens if I change that initial concentration? Does that slope get steeper? Does it get less steep? We're always going to be talking back and referring back to that initial rate of the reaction. So let's look at the rate of this reaction. We did 3 different experiments looking at this production of NO2, NOx gas. The first experiment, we started with these 2 different concentrations of our 2 reactants. And then someone graphed it and found the tangent to the line where it started. They found the initial rate of the reaction. And that's what's over here in the far right column. And then we did it again, but we changed the concentrations, and again we changed the initial concentrations. So look at this data and give your feedback on which one of these statements is accurate for these 3 experiments we have for this exact reaction. And I want you to figure out how to say what part of the data you looked at in order to answer this. Couple more seconds. Talk to neighbors, see if you guys agree. Scoot over and join somebody, would you, cousin? You guys are really, really good at confusing each other. Okay, so can someone tell me, how would you look at this data and try to understand whether changing the concentration of NO had an effect on the rate of reaction? Salma, what are your thoughts? Thomas, you looking it up? Yeah, I'm guessing it's not this. Brianna?
I looked at the concentrations of NO to see where they changed, and then I looked at the concentrations of O2 before I looked at the reaction rate to figure out which of them would be. Because in experiment 2, the concentration of NO doesn't change, but the concentration of O2 changes.
Careful, careful, careful. These are initial concentrations that we start off, right? When we put these things like, okay, ready, go. That's what these two columns are. Is the two columns that I have in red squares right now are what the initial concentration was. And then we let it go and we looked at the rate of reaction.
I said B because I was trying to think of the pre-class quiz and I thought it was kind of proportional to like the bond, or not the bond order, the rate order. So I was kind of.
This relates to rate order. This actually exactly relates to rate order. So then how do we look at this data and try to dig that out of this?
You see like by what percent the NO changes and see if it's the same as how the reaction rate changes. And if it's the same, then it's.
Okay, so let me just make really sure, and maybe we're just saying it a different way, I'm not completely understanding you guys. Experiment 1, we started with 0.01 molar of each of our reactants. Experiment 2, we started with 0.1 molar of NO with a different concentration of O2 that was happening. And then the third one, we started with 0.005 of NO. So the three different experiments, there are three different flasks we set beside each other. We let them go, and we looked at, well, what's the rate of the reaction based on changing some variables. So which two of these would we have to look at in order to determine the answer to this question? Justin?
The third one.
Okay, so we don't just look at the third one, Kristen?
You compare 1 and 3.
Great. So we say, well, what's the initial rate when we have 0.01 molar of each? Well, let's see how that changes if we now have a different initial concentration. Why can't we use experiment 2 for this? Because the NO doesn't change. But experiment 3 compared to experiment 1, the only thing that was changed was the initial concentration of our NO gas. Did the rate of reaction change when we used half as much concentration starting? How much did it go down by?
How much did one go down?
How much did the rate of reaction change when we used half as much to start with?
25 times the amount.
Thomas? Not quite. 10 times would mean 10 to the negative 7th. It's a number. It's not just the exponent.
It went down by a 4.
So it went to a fourth. So we cut the concentration in half, and the rate of reaction changed by a factor of 4. Is that proportional? What's that called? Okay, so this is what we're trying to do. We're trying to see, well, how does the rate of the reaction, how is that impacted by starting with a different initial concentration of each one of our reactants? So let's actually go through and let's first describe what we're going to be, how we're going to be using this. And it all comes back to these differentiated rate laws. So there's a couple of things that we said. We want to know how fast the reaction goes because that will tell us about time in the end. But this equation doesn't have any time in it whatsoever. This equation just relates the rate of the reaction to the concentration of reactants. That's it. That's all we get out of this. It's not until we get to the integrated rate laws that we can consider time. So this is not the most useful equation, but we need to know how to use this in order to then talk about time. So this says, if we know the initial concentration of our reactants, if we have this relationship all set out, we should be able to predict how fast those reactants get consumed, or what the rate of a reaction is. And what we're doing is we're saying that the concentration of each one of our reactants, if we have 2 reactants, this is it. If we have 3 reactants, then we would have concentration of C raised to the whatever x power, that all of our reactants that influence the rate of reaction show up there. And that they're all scaled, that there's some way that they factor in how much they influence or how fast this reaction is overall. For TNT, exploding, that's a really big number. For rust forming, that's a really small number. And sometimes what we find out is that this equation actually doesn't even involve chemicals that we see in the overall equation. Does anyone know why chemicals that aren't in the equation we normally see for a reaction would be included here?
Was it like we were talking about last class, but just like combustion reactions, like NO2 is kind of, or NO, I forget which one it was, it's just kind of like, or N2 is like in the atmosphere, it like kind of like just goes in with it. But you include it just because, just like.
So NO2 might be one that we would think about here. So in the graph, do you remember, what was the first thing formed by the combustion engines? Nitrogen reacted with oxygen and formed carbon dioxide and water and NO. What happened to NO? As soon as it was pumped out, what did NO become? NO reacted with oxygen, became NO2. And then NO2 reacted and formed some ozone later on. Okay, so maybe some of those intermediates actually matter as far as the rate of reaction. So those are the kinds of things that we need to be thinking about. The different things in this equation of this differentiated rate law are K is called our rate constant. A and B would be the reactants. There might only be one. There might be two. It might be three. However many reactants we have, if they influence the rate of reaction, then we're going to see their concentration here. And then the M and the N are relating back to the pre-class quiz you guys did, that those are called the rate order. The rate order that we saw on that last slide, when it's an exponential relationship, what's the rate order for an exponential relationship? Anyone figure that out? 2. So the concentration, if we change the concentration of one particular thing, if it's second order, that means that this is squared. So changing this concentration has a squared effect on the rate of reaction. If it's first order, it means if we change the concentration of this one, we make that change raised to the first power, and that is proportional change in concentration to the change in rate. What if something is zero order? What would that mean? Thomas? So if something is raised to the zero order, anything raised to the zero power is 1. So if we change the concentration, what effect does that have?
No effect on the rate.
No matter what you put here, it's still going to be 1. So that means that changing concentration of alcohol is exactly like this. That's a zero order elimination process. So if we have alcohol really high or really low concentration within some reasonable limits, the rate of consumption or metabolism of that ethanol doesn't change at all. So we're going to be working with simple cases. There are cases where the rate order is 1.5 or 2.75, whatever that is. Experimentally, there's more complicated systems. In our class, these are only going to be 0, 1, or 2. Either it has no effect on the rate, it's proportional, or it's exponential. That's it. And so we can say, well, what's the rate order of the entire reaction? And we just add up M and N. And as much as we want to plug in stoichiometric coefficients for those, we don't. You always look at data in order to determine these. Please never, never, never just take the stoichiometric coefficient, put that as the rate order, because what that is assuming is that there's no intermediates formed in that reaction, and we know everything that's happening in that reaction. If you're really precise in your lab and you know that there's no, it's a one-step reaction, you can do that, but we're not going to in this class. So let's not plug in our stoichiometric ratios. Let's use experimental data. Okay, so let's now enter, I want you guys to find the rate order for both of our reactants. So we're going to be generating this equation here for this particular reaction, okay? So our two reactants are O2 and NO, right? O2, NO. And what I want you guys to do is use the data. This is the same data we just looked at. I want you to use this to determine what M is, the rate order for the consumption of oxygen, and what N is, which is the rate order of consumption of NO, and then click in those two numbers. So if it would be 0, 1, then enter 0, 1. If you're not sure what to do, talk to your neighbors. If you still don't know, raise your hand, please. So do M and N. Sorry, I wrote it backwards on the slide. Do them in order of the equation up here, please. Everyone okay with that? M first and then N? Chelsea pointed out that I mixed it up in the text. Sorry. It may be the same solution. To find the overall rate order, that's just the term we use. That's something we can work on. What is M first? Did you already found it? What is it?
No, I know, but I just want to know what the number is.
That's fine. So we compared two of these experiments, and we said, well, when the only change, so we have this constant, what happens to the rate we already have? So now we need to do the same thing for options.
Oh, okay. I was trying to do it backwards.
So from your
Yeah, I think I was trying to put this in for Terry, and I got the
Oh, okay, sorry, I was gonna because it's
Alright, so make sure you get to the What are you doing? Never, ever. Why did you put 1 and 2? No, you do not. You have to determine experimentally. All right, so let's talk through this. So how do we look at this data and not fall in the trap of using just plugging the stoichiometric coefficients in?
We're not looking at the stoichiometric.
Okay, so the stoichiometric coefficients are important because the relative rate of consumption and production of reactants and products is always tied together with the stoichiometric coefficients. But that doesn't mean that the rate of the reaction overall is tied to how we change the concentrations of those. There's a big difference between those. And if you're not comfortable with what I just said there, come to office hours. We talk through it one-on-one. It'll make sense, I promise you. So how do we use this experimental data to determine how the rate of the reaction varies with the initial concentration of either one of the reactants? Alex, how'd you go about it?
Like, the same thing I did the last time, I realized that that was exponential because, we went from exponential experiment 1 to experiment 3, NO changed by 0.05, and then the initial rate of reaction changed by like 1/4, I think.
Yeah, and I think it's easier for me to look at the lower concentration to the higher concentration. So for me, if you start with not changing one of the two variables, we're saying we're isolating one of the variables. We want to know only what happens if we change the initial concentration of NO. And between experiment 3 and experiment 1, we doubled that concentration. What happened to the rate? So how do these two rates relate to each other? I totally drew over.
Oh. That's a fourth of the other one?
If we go from the bottom to the top, if we compare in that direction, we doubled the concentration from experiment 3 to experiment 1. The rate of the reaction increased by 4-fold.
Okay.
So that means that whatever this change is, 2x raised to the n power, what does n have to be? Do you guys see how that exponent of 2 allows us to say how those two relate to each other?
Can you expand?
Okay? So if, go back up here to our top equation, that we're saying that somehow the rate of the reaction is related to the initial concentration of NO. Everybody okay with that? Just as a mathematical relationship. So if we have an initial concentration of 0.005 here, and we know the rate, and then we change this to twice as much, and the rate goes up 4 times. What does that tell us about this exponent? Does that work or no? Can someone else try to explain it? What's that? Go ahead, Mia.
Well, in order to get the rate to increase times 4, then the exponent has to be 2 because you have to square it to get that number.
So if we had a change of 2-fold in concentration, and whatever that is proportional to rate, it's not just the rate didn't go up 2-fold. The rate went up 2-fold squared. And so that exponent is the rate order. If it went up 2-fold, that would be a first order. It means it's directly proportional. Does that help? Devontae? Okay. So then if we do that for, and I want to say, so then let's do that. So that means our n is 2. So then let's look at 1. Why would we look at experiments 1 and 2 if we're trying to find m? Taylor?
Because after the concentration of O2 was changed, and the concentration of NO wasn't.
Okay, and I just really want to be careful on wording that between these 2 times we did the experiment, we started with a different amount of O2, but the concentration, the initial concentration of NO was identical. Okay? We're not talking about, this is not a change over time. This is talking about starting with a different amount. Is that okay? So then when we look at it that way, the only thing that was changed between these two was we said, okay, let's start with twice as much O2 in experiment 1 compared to experiment 2. Did that have any effect at all on the rate? Devontae? What happened to the rate when we doubled the amount of oxygen present in the beginning, the concentration?
It doubled the rate, so it'd be exponential, it'll be 1.
So,
I mean, not exponential, it's proportional.
perfect. So what I'd say is from that alone, you can say that m equals 1. And we just determined that n equals 2. It happens for this reaction that those are also equal to stoichiometric coefficients, but please use experimental data to determine that. And don't just plug in stoichiometric coefficients. So then what's our rate law? You guys all write out the full rate law now? What is it?
Oh, no, I thought you meant the numbers, I'm sorry.
Nope. Does anyone have the rate law written? What would it be with our m and n plugged in?
Are you saying O2 to
So say the whole thing.
the rate equals
times the concentration of O2 raised to 1. So we can write the 1 if we want. We don't have to.
And then times the concentration of NO squared.
Fantastic.
If you're writing for the rate order of 0, would you write 0 or just not write 0?
Good question. What do you guys think would be more valuable? To see an equation where it says to the 0, or just not to include it? So maybe for us learning, to the 0 is better. But for simplicity's sake, we don't include it because we say that has no influence on the rate of the reaction. So if you ever see a differentiated rate law that doesn't include one of the reactants, what does that tell you? It's 0 order.
But if I just said you could write the 1 or choose not to write the 1, so how would you know the difference?
How would you know the difference for what?
Like if you don't have to write the 0 or and you don't have to write the 1, how would you know if it's 0 order?
So that is first order. Anything raised to 1 is itself. If it was 0 order, it wouldn't be there. Because anything raised to the 0 power is 1, so that means that whole term goes away. That whole concentration is not even written in the differentiated rate law.
So you're saying if it's 0, all we have to write is rate equals NO2 for NO squared?
Concentration of NO squared if oxygen was 0 order, yes. And we'll see some examples of that. And by the way, in these slides, I have about 3 other examples we're not going to work through. So feel free to go through after class, work on those in PowerPoint slideshow mode to make sure that you go through them step by step and try to do it yourself. And don't just see the answer and be like, I get it. That doesn't really work. Okay. So I think most people are getting the hang of it. So 1 and 2. And the way that we say that, just terminology-wise, is that this reaction is first order with respect to oxygen. It is second order with respect to NO. And the reaction overall is what order? The reaction overall is third order. So this is how you typically would see it written out. So you would see, you would not include the 1. You wouldn't include anything that is 0 order. And it's a third order overall reaction. All right, so then I want you guys to figure out what our rate constant is. You have about 1.5 minutes to determine the value of the rate constant for this reaction. How are you guys doing? Snarky comments.
I get it.
Okay, so how do we figure out what the rate constant is? Sabrina, what'd you do? So we have a relationship that tells us how the rate of reaction relates to the initial concentration of the 2 reactants and this K that we don't really know yet. So how do we figure out what this K is? Kira, how do we figure out what this rate constant is?
I have no idea.
Natalie, how do we figure out what the rate constant is?
You have to pick one of the experiments. You have to make sure it's all.
So remember, this is called a rate law. If it's a law, it means it should apply to any set of initial conditions at this temperature. Okay, that's a little caveat. So that means that if we're in experiment 1, that this concentration raised to the rate order times this concentration raised to the rate order times some constant will give us that rate of reaction. And that's true for any of those three reactions as long as they're at the same temperature. So if that's true, then Kira, how do we solve for K? You're going to science the shit out of this. Cosme?
When we make all the concentrations one, like make NO a concentration of 1, and then make NO2 concentration of 1.
So we can't do that yet. We could predict what the rate of reaction would be if we had those, but that's not where we're going yet.
Okay.
Dana?
Choose one of the experiments and then plug in the rate and the concentration.
So I'll just choose experiment 1. So we know that the rate of experiment 1 is 1.0 times 10 to the negative 6 molar per second. That equals K times what? Times the concentration of O2 in that experiment, which was 0.0100 molar, times, raised to the first power, right? Times the concentration of NO in that experiment, the initial concentration is 0.0100 molar, raised to the second power. And then, Kira, how are we going to find the rate constant from that?
Can you just like multiply two right and divide by K?
We just rearrange to solve for K. It's all known values. We could do this for any of the three experiments, and this would work just fine. That's why it's a law. It applies to many different starting conditions. So if we do that, what do we find for this particular reaction? Dana? K equals 1. Okay, what are the units? It's different for every order. Brooke, what did you find?
Well, one of the molars would get canceled out, and then you would still have seconds to the negative 1 over.
So per molar second. And here's the trick, is that if I just give you units, you should be able to figure out what rate order that reaction is. Why? Oh, I think I messed up actually. So on the right side, we have molar squared, molar. On the left side, we have molar per second. So what did I miss? On the right side, it should be
the second to the wait. I mean, there's a second to the second to the negative 1.
So here's the deal, is any units you have on the left side need to equal the units on the right side. Here you have molar cubed, here you have molar per second. So the units of K cancel out any units you have on the right to equal the units on the left. Is that right then? Per molar squared second. And we can do this for any different rate order of the reaction. All right, I'm going to have you guys look at that as we go forward. Quick question?
Why isn't it 1m squared over s?
Because if it was m, then we would have m squared times m squared on the top. That doesn't equal m molarity. So the units on both sides have to equal each other out. So the units of K are made in order to convert our units on that side to be the same as the other side. All right. So we can rearrange all of this. And 1.0 would be what I'd want to see because we have 2 sig figs. I guess it depends. Is it 1 or 1.0? What's the right number of sig figs? Why? How many sig figs is this?
2.
This is 2 sig figs. Did anyone use experiment 2? Experiment 2 is only 1 sig fig, so that would have limited your sig figs. So it depends on which experiment you use, you would have had a different number of sig figs.
If you were given all three, and you did use one, would you still have to do 2 figs?
No, you're always limited by your weakest link.
Okay.
If you said I use experiment 2, you would only be allowed to say with 1.
But if it's given values and people looking at your data know what experiment 2 was, shouldn't it be like for it to be proportional 1 to 2? So
Yeah, so if I was a better scientist and I was writing this table, I wouldn't report shitty data like this that didn't give me enough accuracy to hold enough significance. Yeah.
Since we determined that the rate order for NO is 2 because of the exponential relationship, wouldn't K also have an exponential relationship?
Nope. So K is always the proportional factor. So what I was trying to say earlier is, someone asked me, is this always the same number? And this is absolutely a different number. We're going to talk about the radius equation in a couple days, and that tells us, well, how does temperature or activation energy affect this reaction? This is how it links together activation energy. If we have a catalyst, this number goes down. If we warm it up, this number goes down. If we have TNT exploding, this number is really big because it means that you don't have to have much of these for a really fast reaction to go. Or if we have something rusting, it takes years for stuff to rust. And so that means that this is going to be a really small factor, that even though we have a lot of these reactants, the rate is going to be really slow. So this tells us we can make predictions. We look at 2 Ks side by side. We can say, well, I know this reaction is going to be faster because it has a much bigger K. Does that help?
Yeah, I'm asking because I did the K value for experiments 1, 2, and 3, and the values are all there.
So if you did you square your concentration of NO?
Yeah.
So I have to take a look at that after class. Did anyone else do multiple experiments and get different values? You got different values as well? How close were they?
Well, I don't know if I just did it wrong, but for experiment 1, I got K equals 1, and 2, I got K equals 2.
K equals 1 versus 2?
Yeah.
And then for experiment 3, K equals 4.
So that's not good.
That's why I was asking if it's an exponential relationship.
No, it should not be. K should be constant. So let me take a look at those numbers afterwards. I've never gone through all of them and compared them for this specific set of data, so maybe there's something wrong with this data. It comes from our textbook. All right, let's try this with another experiment. All right, and you guys all know this already. 0 first and second order. You can come back here for some definitions. So we talked really briefly about what changes how fast a reaction occurs. What are some major factors that influence the rate of a reaction? Concentration. If we have a different concentration, the rate might be different. If we warm it up, we speed up reactions. What else? If we add a catalyst, if we let those reactants come together more easily, maybe we give them a surface, then now they're touching each other instead of trying to find each other in space. Any other ideas?
Does weight have to do with it at all?
So I would say weight would go to concentration, and if you have more of it there, then you have more of the reaction. Any other ideas for things that influence? Pressure. We put them closer together. Yep, which you could say for gas would be concentration too, right? Okay, so some of the major factors are time, temperature, concentration, unless it's something at 0 order, in which case concentration doesn't matter, and adding a catalyst. Surface area 2. If we think about burning fuel, burning gasoline, why is it that in our engines it burns so much more efficiently than if you had a bucket of it and lit it on fire? What is it about fuel inside of an engine that makes it all burn so much more rapidly?
I was just thinking it might have smaller surface area than the bucket.
So if you think about taking the amount that's inside of a cylinder in our engine and the amount if you put it as the liquid, that amount would have a much larger surface area if we make droplets of it. Think about how much surface area a droplet has as opposed to if you have a whole bucket of liquid. And all those particles, if you aerosolized it, if you made it into a mist, it would take up, the bucket would take up the size of this building, spreading those droplets out. So it would have a lot more surface area. And the same kind of thing happens, like when you're burning a log, right? You guys ever use those fake logs? Like the starter logs? When you want to go home for the night, how do you speed up that reaction? How do you make it burn out quicker? You ever do this? You take it and you poke it, and you give it a lot more surface area, and then it burns out really quickly. All right. So I want you guys to go ahead, and you can check out this really cool reaction in the top right corner. This is actually what happens when you do this iodine clock reaction. And I want you to click in the rate order for all three reactants. And then you guessed it, you have to find K as well. And so the order is I want you to type in 3 rate orders. Even if one of them is 0, I want you to include it for now.
Is it M or B for O2? So
M is 1.
Yeah, and then N.
So make sure that everything lines up. So that is not that.
Oh, that's what I
So
said.
you can put this on. So just make really certain that you plug in one reaction.
I put 2 and 3 divided by 2.
I understand what the last one was, I don't see why this is
Always determine your All right, guys, I've seen multiple people do this. Can you just take the stoichiometric coefficients and plug those in as a rate order? No! Oh, wait. Sorry. Okay, so figure it out experimentally.
trying to make sure I'm right, which is not possible. For H2O2, I use these equations because everything is the same, like except for these rates. And I saw that this one doubled, and that the initial rates for this rate doubled as well. So I said that since they're both like 2, it's proportional. The same thing for I, and then for H plus, I said it was 0.
You gotta be really careful which experiments you compare, right?
Yeah.
Because you can only compare two experiments where one variable is changed,
Yeah.
and that's when it gives you insight.
So for this one, I use experiment 1 and 4.
Because everything else is the same.
Yeah.
And the rate of the reaction?
Well, the rate didn't change, so I said it was 0.
Perfect. All right, if you find the rate order for all three, then find the rate constant as well. How are you guys doing? So you're only clicking in the rate orders. Okay. All right, so let's bring everyone together and let's talk through this a little bit. I want to know, does the rate of this reaction have is there any effect on the rate of this reaction if I change the concentration of hydrogen peroxide? How do I figure that out? Experimentally, let's not look at this data for a second. Experimentally, how do I figure out if the reaction between hydrogen peroxide, iodide, and H+, if the rate of that reaction is influenced at all when I change the concentration of hydrogen peroxide?
Change the concentration, see if the rate is faster.
Change the concentration of what?
The hydrogen peroxide.
Only the hydrogen peroxide, okay? That's the key to looking at this experimental data. We say, well, I'm going to do the experiment multiple times, but if I want to look at how hydrogen peroxide influences the rate of the reaction, I can't change anything else. I saw a lot of people starting out by looking at comparing 1 to 2, 1 to 3, 1 to 4. You have to look at specifically, well, let's look at two experiments where only one variable was changed. And I think most people ended up kind of getting there. So what did you guys decide about hydrogen peroxide? Does it changing the concentration of hydrogen peroxide have any influence on the initial rate of reaction? Which experiments did you guys look at? In experiments 1 and 2, if we look at those, the only thing that was changed at the start of these reactions, the only thing that was different about each run, was that we had a doubling of the concentration of hydrogen peroxide to start experiment 2. We see that that changed the rate. Initial rate of reaction went up. What's the rate order of hydrogen peroxide based on this data, Chelsea? It's not 1.15. Someone help her out? Here?
Can you just repeat the question one more time?
Based on this data, when we double only the concentration of hydrogen peroxide, we see that the rate of the reaction changes. So what rate order can we say that hydrogen peroxide is in this reaction?
Would it be 2?
Why?
Because the initial rate doubles as well. So this is where I got stuck.
Okay, so if we go back to, maybe I'll do it this way actually. If we're to write out a reaction, and we say that somehow the rate of reaction is, there's a whole bunch of other stuff here, right? But if we change concentration of hydrogen peroxide, that may have an influence on rate. So in this case, we doubled the concentration of hydrogen peroxide. What happened to the rate?
Would it also double?
It doubled. So that's the change of hydrogen peroxide raised to what power? 1. Because this change is equal to this change. Twofold change, twofold change.
Okay.
So that would mean that our rate order, our reaction is first order with respect to hydrogen peroxide. What about for iodide? Javante, what did you do to figure out the rate order for iodide?
I compared experiments 1 and 3 because those were the only experiments where the other two concentrations for hydrogen peroxide and hydrogen were the same. And I saw that from experiment 1 to 3, the concentration of iodide doubled, and the rate
Great. So it's a first order reaction with respect to iodide as well. And then who wants to talk about H+? How do we figure out whether H+ influences the rate of reaction? Chase, what'd you do?
You look at experiments 1 and 4.
Okay.
And you see when you change the concentration of hydrogen plus. That the overall reaction rate does not change. So you would find that its number would be 0.
The rate order is 0 with respect to H+. So then you guys all clicked in all 3 rate orders, 1, 1, and 0 respectively for the different components. So its overall rate order, I'm not going to have this as a clicker. 2. All right, so then I want you guys to go ahead and, this is our differentiated rate law. Why do we not include H+ in this equation? It's 0 order, so it's redundant to put it in with a raised to the 0 power because it's never actually going to be calculated. Okay, so I want you guys to click in what the rate constant is. I'm going to give you 1 minute to find the rate constant for this reaction, and then there's another couple slides that we have to get through. All right, Pat, how are we going to find the rate constant? Which experiment did you use? Okay, so if we choose experiment 1, these would be our values raised to the appropriate rate orders. And then we'd rearrange for K, and we'd find 1.2 times 10 to the negative second per molar second. Those units should be really careful with those to make sure that they come out. And if we rearrange it the way I did here, it's a little bit easier to see that molar cancels out, and then we have per second and per molar written out there.
That's not what I got.
The value you got was different?
Yeah.
What'd you get?
It was, it would be 1.15 times 10 to the negative second.
How many sig figs should we have?
Never mind.
Thanks, Chase. Appreciate you pointing that out.
I used to want, like, exact value.
Yep. We want exact values, but we got to be sure we limit it based on how accurate our data is. Okay, so I want you guys to go ahead and click in what's the rate order for this reaction.
I know that you're supposed to set ground in order to get figures and that'll make it accurate, but how accurate is
Talk about it after class. Okay, everyone clicked in your rate order for this reaction? What? What? Okay, so there is one way you could have answered this question. What is the way you could have answered this question without knowing anything else? Let's see what we got. Ooh, some of you got it right. I'm sure that wasn't chance. Okay, radioactive decay is always exponential, which is second order. Okay, can you give me like 30 more seconds? So what we're going to be doing in class on Tuesday is we're going to be taking that data that we just had, and instead of just having a table of data with concentration versus time, what we're going to start doing is we're going to say, well, there's some trends. When we start looking at all 0 order, this is original concentration versus time data. And this holds true for every 0 order reaction. If you look at the concentration versus time, and then we're going to say, well, let's manipulate this data. Let's also take the natural log of that concentration. Let's also do 1 divided by that concentration. And this data, here's one data point, just plotted in a couple of different ways. If we take all of that and we plot each one of those graphs, each way of looking at that data a little bit differently, we start to see some really stark trends. We can visually look at these 3 graphs and immediately say, I know what rate order this is if we plot concentration versus time, the natural log of concentration at each one of those time points, and 1 over concentration at those time points. So this is what we'll start class on Tuesday with. You guys are going to have to do a little bit of reading before then on integrated rate laws. There's 1 or 2 questions on your homework. Come in ready to go with integrated rate laws and thinking about how time influences concentration. Thanks, guys.